Okay guys, here are the losses and power flow diagram of the induction motor. Okay, we can see that we have a P in. P in is equal to, because this is a 3-phase, so circuit 3 times V terminal times I load, which is come into your system, plus cos theta. Sorry, times cos theta. So after you minus all the related losses of stator, copper loss, the core losses, and so the losses here is regarding your, we have here the source coming to your stator. So this is your rotor inside. So all the losses here is happen on the outside, means on the stator side, and on the stator copper loss, then core loss, the windings here, and after that we have the rotor copper loss which happen here inside the rotor, which happen inside the rotor. Between the air gap, we have the air gap power, the power that deliver from your stator into your rotor. The air gap here, we have another copper losses, rotor copper loss. Means that the copper or the aluminium cage and losses. And then we have the, after converted into the shaft, and so the losses happen on the friction and windage, and the miscellaneous, which is so called as the stray loss, the percent of the losses compared to the full load rating or full load power range. So the friction loss here happen to the bearings. Bearings and the friction happen between your stator and rotor. Then after we minus all the related losses, so we get our P out. So P out is equal to P in minus P losses, same per previous design or previous system in DC. So all the losses here we sum together in terms of P losses, P total, P in minus that P losses, we get P out. Okay, in terms of concept, actually the induction motor is just same like our transformer. So we have here transformer, it comes from AC source to primary coil, then transfer to secondary coil. Just the matter is that the induction motor, we have a short circuit secondary. So what happens that instead of we are transferring the energy from electrical to electrical, now we are transferring energy from electrical to mechanical. So it means that we are rotating this secondary part, and we have a high current that flows into the secondary wiring or secondary circuit. So the current will push the secondary to turning device or turning mechanism. Okay, if you take a look at the notes, you can see the per phase equivalent circuit of induction motor. We can represent same per transformer kind of a circuit. And if you simplify the circuit in per phase equivalent circuit with losses and the converted power elements, so we can label all the elements as the P core, core losses, and the stator losses, and stator core losses, our core, mechanical, P stray, and this is PRCL here. We have PRCL in between your P gap and P converted. Then we have PRCL, and all of these elements we can calculate based on the resistance and the impedance that we can get from the equivalent circuit of your induction motor. So actually the losses that we have now Sorry. So if you follow or you refer to the power flow diagram, you can see that the P out is equal to P conversion minus P mechanical and also minus P stray, and also minus the P A gap and P in. Sorry. P out is the amount of P conversion that we obtain here at this point, minus P mechanical and P stray. P mechanical is your P friction and windage, and P friction and windage. But this P conversion is equal to P A gap minus P RCL. P A gap minus P RCL, rotor copper loss. And meanwhile, your P A gap is the amount of P in minus P stator copper loss, also minus P core. So here are your the flow. From the flow diagram, you can generate the equivalent or the power equation. So we shall go through deeply and discuss up to the answer this coming Thursday. So I hope we can review the notes first, and we shall calculate, and we shall go deep into this calculation per the example inside the book. Okay, thank you for this session, and we meet again.